Okay, these are some kind of notes for section 7.2. And if you look over in your textbook on page 390, I'm just going to kind of use some of the sketches in the textbook to save a little bit of time and effort here. And what we're going to do is we're just going to try to find the area between these two curves. This might be f of x, and this might be g of x. So again, following our same pattern of Riemann sums, we're going to break this up into little measurable units. In other words, we have an irregular, an irregular, which is we can't measure also because we don't have a technique for finding the area of this region, let's say from A to B, between these two curves. It's a very, unregular type form. So how are we going to find the area? Well, what we'll do is we'll use little measurable forms that we have, in this case rectangles, to approximate that. And the more rectangles we have, the more closer we'll get to the actual area between these two curves. So we're using areas of regions that we know, rectangles, to approximate the area of a region we don't know. That's whatever this is between these two curves. That's this whole technique. And we're using the Riemann sum process. So again, each of these rectangles will have a width of delta x, but they'll have a height of whatever this is going to be. And if we pick some c sub k in this region, in this subinterval of the particular partition, that's how we divide this up, we call that c sub k, and then the actual height will be the top curve minus the bottom curve. And if this is positive and that's negative, a positive minus a negative is a positive, so we just actually add this length to that length, and we'll actually get the height of that rectangle. So we're just summing these all up. So you can see up here, this is basically the general idea. This will be f of c sub k minus a g of c sub k. That's going to give us the height, and here's a kind of a typical rectangle here. That will give us the height. And they have that over here, so you can look in your textbook if you can't read it. And then delta x will be the width. So we'll set it up like this, and we'll take a summation of all those, and then the limit of these as delta x goes to 0 is just the integral from a to b of this f of x minus g of x dx. So we're following the same pattern that we established back in chapter 5 for these Riemann sums. And then down the bottom they give you a gray box. This is a little bit more general because we can also take the area between the curves with respect to y. We'll see that later. So I wrote these up in these notes that I made up. And you can take a look at that. So to find the area between curves, one in terms of x, the area would be x equals a to x equals b. These would be the limits in terms of x. And that would be f of x minus g of x. In this case, this is the top curve minus the bottom curve. Okay, this is the top curve minus the bottom curve. Okay, and then that'd be easier to see if I put this on the backings here. This makes it a little better for you. There you go. Okay, it's a little easier to see with the backing like that so it doesn't bleed through. Okay, so this is the top curve minus the bottom curve. Now, if we do this in terms of y, which we can also do, and we'll see some examples of that, then this would be the integral from y equals c to d. These are just two other limits of integration, but in terms of y equals, and this would be the right curve minus the left curve. And this is the different functions, h of y minus k of y, which would be the right curve minus the left curve. So these are going to be the two techniques we'll be primarily using to find the areas between two curves. Okay. All right, here's, we've got some examples. I'll cover the examples in the book, then I've got some other examples here. Let's see, this is one example you could look at. Example A, find the area of the region between y equals x squared plus 2 and y equals x from 0 to 2. So this would be my f of x, the top curve, and this would be my g of x, the bottom curve. Remember, y equals x is just a diagonal line, and then x squared is just a parabola shifted up 2, so this is our parabola. And we want to find the area of this region. You see we got a parabola on the top and a line on the bottom between 0 and 2. So that's not too bad. So we just set this up, top curve minus bottom curve, top curve minus bottom curve. And then we're just going to integrate from 0 to 2. And that's just the extension of the Riemann sum. You don't have to write it down. You can just use this basic formula I gave you up here to start. Top curve minus bottom curve. Okay. And the top curve was x squared plus 2 minus x. And then I just put this in a descending order. You don't have to. You could either way you can evaluate. It doesn't matter. X squared minus x plus 2, the integral. And then if I take the antiderivative of x squared, remember the antiderivative of the sum or the difference is the sum or difference of the antiderivatives, and the same with the definite integral of the sum or difference is the sum or difference of the integrals. So this is going to be x cubed over 3 minus x squared over 2 plus 2x. Now when I evaluate this, if I evaluate this at 0, remember we're going to take this number, remember it's going to be f of b minus f of a, using the second part of the fundamental theorem of calculus. This is the f of b, that's the f of a. Well, f of a, if I put 0 in here, this is just going to 0 out, so I don't even need to consider that, but I can put 2 in here for the f of b. So that's what this is. So 2 cubed is 8, so it's 8/3. 2 squared is 4 over 2. And then plus 2 times 2 is 4. So this ends up being 2 2/3 minus 2 plus 4, which is 4 2/3. So that's the area of the region. Not too difficult. Okay. Alrighty. So I hope that helps. Again, take a look we'll do some more of these in the next part of these notes. But make sure you kind of take a look at page 390. Have your book out because I'll refer to that as I go through these notes, etc. And just kind of go through the theory, but basically the formulas I gave you are what's going to work. And then we'll see lots of examples.